This is the second test corrections video. This will be questions 9 through 15. These are the calculator questions, so make sure you have your calculator out. And same drill as before. Rework the question from the test. Really rework it. Try doing it without looking at the answers even to get that extra practice in. Solve the practice problem I provide and make up your own. So let's get started. Question 9 on the test said the graph of this function changes concavity at blank. The best possible way to do this would be to put this function into your graphing calculator to get a sense for the concavity change. Now, since you can't actually calculate the concavity change directly, I would then put the first derivative function in. A function's concavity changes when the first derivative goes from increasing to decreasing or from decreasing to increasing. In other words, where the first derivative has a max or min. So when I graphed the first derivative, it turned out that it had a minimum value at negative 1.89. And I found that just by using the calc function. So second calc, and then you choose the option for finding the minimum because I looked at the graph and saw the minimum. Try one just like it. Great, so this was C, and what you'd have to do is find the first derivative. And in this case, I did it a slightly different way, which is I found the second derivative, and I figured out where the second derivative equals 0, because that's what a point of inflection is. And I used the second derivative test just to show that it really only changes concavity at 3. Even though both 0 and 3 are inflection points, at 0, the function's concavity doesn't change. It briefly hits a saddle point, but it actually continues concave down even after that saddle point. So 3 only. You also could have done this by graphing the first derivative and looking for the max and min values. Here's the next one. Question 10 asks for the minimum value of the product. So this is actually an optimization problem, but the quickest way to do it in your calculator is once you've got that function, the function for the product, if you put this function directly into your calculator without taking a derivative or anything, you can see the maximum point, and you can just figure out what the point is, and the y value of that point turns out to be negative 8. Again, that's just second calc using your calculator to save you some time. Here's one for you to try. So this is almost exactly the same thing. In this case, I showed you the algebra, but really the quick way to do this would be to do it in your calculator. You start with a function for the thing you're trying to optimize. You work with the given information to get that function as a single variable function. And then you find the critical points, or you can just graph this expression right here and find the maximum using your calculator. Since it's asking for the maximum value of the product, the answer is the y value of that maximum point. Question 11 is a linearization problem. What they give you is a point on the original function, 3, 8, and the slope at that point, which is negative 4. And then they ask you to find the f of a nearby x value. So what I did was I created a linear equation using the given point and the slope of the tangent line. And this is just point-slope form. And then I solved for y just to get this in function form. And I plugged in the new x value, the nearby x value for x, and I got my approximation. Notice that this allows you to approximate f even without knowing what the function f is. Try this one just like I did. And here's the work. Again, using the calculator, you can save yourself some time for this one. The correct answer was A. Let's look at number 12. 12 says for what value of C on the interval from 0 to 1 is the tangent to the graph of this function parallel to the secant line. So don't get distracted by the work yet. Think about what the meaning of these words mean. The strategy is really testing whether you can read and understand a mathematical statement. So our answer is going to be an x value that's somewhere in between 0 and 1. So notice you can immediately rule out this negative number because it's not between 0 and 1. And at that x value, the tangent line of this function is parallel to the secant line. Tangent line's pretty easy. I think most of you will realize that the slope of the tangent is just the first derivative, and we can take the first derivative of this function fairly easily. The slightly more difficult is to understand what the secant line is. And so a secant line in this case is talking about the secant line of this interval. In other words, the line that connects the two endpoints. The endpoints of this interval are 0, 1, and I got that because 0 is the x value, and I plug in 0 to this function to get the y value, which turns out to be 1. And 1 comma e minus 1, and that comes from plugging in the second x value to the original function. So I can find the slope of the secant line using y2 minus y1 and these 2 points. It turns out to be e minus 2 over 1. And then I can find the slope of the tangent line at any given point just by taking the derivative function, which is e to the x minus 2x. Remember, the derivative of e to the x is e to the x. So I set these two equations equal to each other, and I'm actually ignoring this now because I just used the simplified form. I can solve this equation manually, or if you use your calculator and you put this expression into y1 and this expression, which is really just a number, into y2, remember to use parentheses on the top. If you find the intersection point of these two, you've got the x value that is the solution to this equation. And that's just the technology way to answer this quickly. It turns out to be 0.351. See if you can do the same for this question, and do your best to use the calculator to help you. Here's a quick look at how the work would look. Notice I got the two endpoints, which are 0 ln of 4 and 4 ln of 20. And I would just keep these as ln so that it stays as accurate as possible. And I can calculate the secant line slope like this. And then I set this equal to the first derivative in my calculator. I don't even show the work here. And it turns out there are two places where those two lines intersect with each other, and both of those places are going to be solutions to this question. Question 13 was one of the most missed questions on the exam, which I was really disappointed about. So maybe you were just thrown off because it was an unfamiliar question style. Notice how easy this is going to be. We identify a function g of x as f of x squared. So notice already g of x is a function that depends on another function. You should be thinking about compositions. You should be thinking about chain rule. And then we've got a particular point A, and it says at this point f is increasing. The best thing you can do for yourself is the second you read that, interpret it in terms of the calculus. If the original function is increasing, it means the derivative at that x value is positive, in other words, greater than 0. It also says the original function is concave downward. Of course, that means the second derivative is negative, while g is decreasing, which means that at that point, g, the derivative of it, is negative. And then it asks you what describes g at a. Well, obviously we know it's decreasing, but now they're asking about concavity in addition to decreasing. So we need to know something about the second derivative of g. So here's my g function. The first derivative of g, just generically, not at a single point, is going to be a chain rule. If I take the derivative of both sides, g prime of x equals, the outside function is something squared, and the derivative of that is 2 times the something. And the inside function is f of x, so you multiply times f prime of x. That's the chain rule right there. And then we take the derivative of this to get the second derivative of g. And the derivative of this is now a product rule because you have a function times another function. Product rule says u dv, the derivative of f prime is f double prime, plus v, which is f prime of x, times du, which would be the derivative of 2 times f of x. In other words, 2 times f prime of x. The two f primes, the one that came from v and the one that came from du, become f prime of x squared. So this expression is an expression for the second derivative. Now, look at all the different details we know. We know that the derivative of g of x at a has to be a negative number. In other words, this whole expression has to be a negative number. But we also know that f prime of a is positive. That's this fact right here. So if this whole thing is negative and this piece is positive, it means that f of x has to be negative at a, which means that this right here has to be negative. So we use this expression to figure out that this has to be negative. And we know that f double prime of x is negative when we are talking about at a. And this definitely has to be positive because it's something squared. It doesn't even matter what f prime of x is. So we have a negative times a negative making something positive plus another thing positive, which means g prime of x has to be positive. Sorry, g double prime of x has to be positive, which means g has to be concave up, at least at that a value. It's just a matter of kind of piecing all the details apart and trusting really that you have the information you need. If you trust yourself that way, you will keep going until the idea strikes you. Try this one. Here's the thinking process for this example. Again, I started with g. I identified that f is positive means f prime of x must be, f of x is positive, and decreasing means that f prime of x is negative. When I took the derivative of g, I used a chain rule. The outside function was something to the -1. The inside function was f of x. I didn't actually write that down, so write it down if you don't see where this came from. But when I take the derivative of the outside function, I get -1 times something to the -2, and I multiply times the derivative of the inside function. This is the same thing as -1 over f of x squared. Since f of x is positive and since it's being squared, the denominator here is positive, which means with the numerator being negative, this whole thing is going to be negative. And since f prime of x is also negative, we've got a negative times the negative, which means g prime of x is positive, which means g is increasing. All right, we're getting there. Question 14 is a pretty fun one. It's actually much quicker than you may realize when you first look at it. We're talking about a local minimum. It says this function has a local minimum at x equals 3. That means at x equals 3 we must have a critical point, which means that the derivative function has to equal 0 when I plug in 3 for x. So I take the derivative and I treat c as a number, right? Because we're just trying to figure out what the constant value of it is. And when I take the derivative of this, the derivative of x is 1. The derivative of c over x is negative c over x squared. Again, try using chain rule. Think about this as a negative exponent. If I set this equal to 1, that means that if I set it equal to 0 and then bring the 1 over, 1 must equal c over x squared. Cross multiply, x squared equals c. And then when I plug in 3 for x, it turns out c has to equal 9. Try this one the same way. And since this is literally the same question, you should see the work is almost exactly the same here, just the little matter of the 2 that you have to factor in. Last question in this section was a nice little velocity graph, just interpreting what it means. So notice this is the velocity, which means we're going to think of this as the first derivative graph. And we're talking about the time from 0 to 8. When the first derivative is positive, this whole place, it means the bug is traveling away. And then down here, when the first derivative is negative, it means the distance is decreasing. In other words, the bug is traveling back towards where it started. The bug changing direction is going to be when the velocity equals 0, because that's when it goes from increasing to decreasing, and when velocity that's when the original function goes from increasing to decreasing, which means the velocity changes sign. And that's why the answer is C. I don't have a practice problem for this last one, but you should be able to create your own, just create a different kind of graph. You could, again, ask about changing direction. You could also, if you want to be tricky, ask about when it starts to slow down or speed up, because that's going to be the max or min of the velocity function. So at this point right here, the bug starts to slow down because the velocity goes from increasing to decreasing. And at this point, the bug starts to speed up because the velocity goes from decreasing to increasing. That's it. Go ahead and create your examples.